Okay, so our last class technical glitch. So we are again starting from where we ended up. Okay, so let's get started. So the last question what we were discussing was like this. So question 1 of today. Okay, boron, carbocation positive, BH. Then it was nitrogen, NH, then positive. Then it was both methyl, then positive. Then there was nothing. You can say 2 hydrogen. Okay, was nothing. So in first case, you can see this is anti-aromatic. The second case, nitrogen lone pair is there. This is aromatic. Next, nitrogen lone pair can donate like this way, and this will create an aromatic structure completely. Here, aromaticity is not there, but here in this hydrogen can be donated as hyperconjugation plus H. But here the carbon-carbon bond do not show hyperconjugation, right? So here no hyperconjugation. So here anti-aromatic, that will be least stable, A, B, C, D. Anti-aromatic, so least stable, least stable. So A will be least stable. B will be most stable among C and D, as D has hyperconjugation. So D will be more stable than C. So this will be order. Then uh, okay. Sorry. Then second question. Second question. I am going to write different groups at para position of any carbocation. Suppose this is carbocation CH2. Then this is benzene ring. So I am going to give different group. Okay. I am going to change these groups, and you have to tell me what will be the stability. In first case, first example, the G group is CH3, CD3, CT3. You have to compare this with this, the stability of the carbocation. The second example, CH3, CHME2, Me for methyl, CH2Me. Second one is CH2Me. Then CHME2, then CME3. One hydrogen is getting replaced by one methyl simultaneously. Third example, NO2, OCOCH3, COOCH3, CH3. So question number 2.A, question 2.A, question 2.B, question 2.C. In first case, how can we compare? How can you compare? CH3 group will show here, suppose carbon, hydrogen. Okay, this will show here hyperconjugation, and thereby it will stabilize the carbocation. So hyperconjugation, methyl hydrogen will show more hyperconjugation than deuterium than tritium, you know. So CH3 will have more hyperconjugation, so more stability it will provide. So from below to above, from bottom to top, stability will be increasing. Next one, CH3, 3 hyperconjugation, CH2, 2 hyperconjugation, 1 hyperconjugation, no hyperconjugation. If you compare with plus I effect, then last one will seems to be more stable. CME3 is more plus I among all the 4. Okay, so this seems to be most stable, but CH3, it has most hyperconjugation. So this is most, this will show stability by plus I. This will show stability by plus M. So plus M is more prominent. So more the number of alpha hydrogen, more will be hyperconjugation, and more will be the stability. So here we will consider the plus M only, not plus I. So from bottom to top, stability will increase. Next one, NO2. NO2 is electron withdrawing group by minus R effect. So it will withdraw electron from ring. That will increase the positive charge. Okay, that will unstabilize the system. So NO2 will be least stable. If we name it A, B, C, D, then A will be least stable. Then OCO-CH3, O oxygen lone pair can give electron to the system and thereby stabilize the positive charge. This is plus M. Here, and this is also COOCH3. That means C double bond O, O, CH3. This is ring. So it is also electron withdrawing group. But NO2 is very much more electron withdrawing group, very much more minus R effect it has than the COOCH3. So this will unstabilize, but not that much as NO2 does. So C. Next comparison of B and D. D will stabilize by plus H, hyperconjugation. B is stabilized by plus M. So mesomeric effect is more prominent. So B will be more stable than D. So this is how this works. And this is how the stability order looks like. Next, another concept. Third question. Now I am going to give you examples that are from different standard books. Okay. So suppose cyclohexane positive versus benzene positive, which is more stable? Guess your answer. 1, 2, 3. Let's go to the answer. First one will be more stable because here the positive charge is on carbon with sp3 center. sp3 carbon, that means it was initially cyclohexane. That means it was initially sp3, and this center, when it was not positive charge, when it was not carbocation, then there were hydrogen, we can assume. So this was sp2. Okay, from sp3 and sp2, sp2 carbon is more electronegative. In sp2, percentage S character is high. That means electronegativity is very high. More electronegative system cannot hold positive charge. They prefer negative charge. More electronegative system prefer negative charge. So here, this system, this positive charge on benzene, this is more electronegative. So this will not easily hold that positive charge. It will hold it by sp3 carbon. Okay. So first one is more stable. Similarly, the same type of example, C triple bond C positive, it will be less stable than C double bond C positive than C single bond C positive. Similarly, more the S character, more the electronegative the species, and less it will be prone to hold the positive charge. Okay, so this is how the stability order you can guess. Two very much. Let's go to another page actually. It is not possible here. I can't get the option. Okay, I'm wiping out this. And again, we are starting. Okay, with the next example. Okay, next example. Suppose this is positive charge. No. Okay, this is positive charge. This is oxygen. This system versus similar system with sulfur. This is very good example. Which one is more stable? Second question will be similar. Oxygen. This is negative charge. Sulfur. This is negative charge. Which one is more stable? This is second question. So let's find the answer. Okay. In first question, sorry, where is the pain? Okay. In first system, oxygen with its lone pair can show plus M. sulfur with its lone pair can show plus M. But when oxygen is showing plus M with carbon, that is 2p of oxygen and 2p of carbon. So 2p 2p overlap. Here 2p 3p overlap. That is less effective overlap. So this will least likely to form. So more stabilization will be done by oxygen with plus M with 2p 2p overlap. So first one is more stable. But in the second case, though it is not concept of carbocation, but it's carbocation, but let's discuss in the same place. First one here, the second one will be more stable because the negative charge can be delocalized or can be donated over the vacant 3d orbital of sulfur. So 2p to 3d donation. But there is no such 3d orbital available for this oxygen. So for such donation is not possible. Here only minus I effect will give stability. Minus I and here minus M. Okay. So minus M will be more prominent. So that's why second one will be more stable. Second carbanion will be more stable. Okay, next one very beautiful question. Suppose this one, and this one. Suppose phenyl, hydrogen, hydrogen. Phenyl, phenyl, hydrogen. Phenyl, phenyl, phenyl. Carbocation, carbocation, carbanion. Stability order, phenyl ring will undergo resonance. This is benzylic position. Benzylic carbocation is more stable for resonance of benzene ring. So first one is very much stable, second one is more stable, and third one is further more stable. Is it so? Yes, obviously it is. So stability order 1 to 2 to 3. Okay, increasing. But here the glitch is the order is absolutely okay. Nothing wrong in that. But the increment of stability from 1 to 2, if it is 100 times more stable, if 2 is 100 times more stable, or a stability of 2 is 100 times more than 1, then the 3 will be not that much stable than 2. It will be more stable, but not that much of stability increment will occur. Suppose it is 10 times more stable. Okay. Why this is phenyl ring. Let's draw this system a little bit. Suppose this is the system. Above the plane, below the plane. As this phenyl ring are bulky. Okay. So all this phenyl ring cannot come at a particular plane for undergoing simultaneous resonance. All these three have to come in a particular plane. But as there is a repulsion between orthohydrogen, it is not possible. So this orthohydrogen repulsion cannot let the system to be planar. Rather, it is at a particular time only 2 ring can be on the plane, and the other ring will be some above the plane or below the plane, right? So this is called actually propeller shape. Suppose this part is above the plane, this part is below the plane, this part is above the plane, this part is below the plane. Okay, so this is kind of propeller shape. You can you have seen in photos like propeller of aeroplane or a propeller of fan, 3-blade fan. Okay, that is not in fan. In 3-blade fan, all the blades are not in plane, rather it is little tilted. So here this due to this tilt, proper resonance is not happening. A 2 ring can be planar at a time, but third ring cannot be planar at a time. First time, suppose 1 and 2 ring is undergoing resonance, 3 is not. Then 2 and 3 is undergoing resonance, 1 is not. So alternatively, all the ring undergoing resonance, but not at a time. Okay, so this is stability. So stability increment we expecting more than this, right? But for this popular shape, the stability increment is not that much. Okay, this was our discussion. Next, our next discussion will be based on a particular question. The question is, here all the electronic effect, your concept of all electronic effect will be failed. Okay, plus third example. If you look upon alpha hydrogen, here all the groups are same, 2, 2, 2, 6, all three has 6 alpha hydrogen. So structure A, structure B, structure C, all have, you can see, 6 alpha hydrogen. Inductive effect is also similar. And then how will you compare the stability? From A to B to C, what we are doing basically, from A to B, you can assume we are giving a knot. Okay, we are binding these 2 points at this position, and from going B to C, we are binding these positions to it, right? So more we are going A to B to C, we are basically binding the terminals, and we are making it more rigid. A is most flexible, C is most rigid. Okay, it cannot undergo flexibility, it cannot show flexibility, as we have bounded it in this way. So this is not flexible, rather this is rigid. A flexible system can undergo planarity easily. A carbocation is planar, you know. So for a carbocationic stability, it is essential that it could attain a planar stability. Otherwise, it is not stable. It will deviate from its hybridization. It will deviate from its geometry. That is not expected. So first one, as it is flexible, it can easily undergo the planar geometry. It can easily attain the planar geometry. But second one cannot do so in the same way. Third one is again cannot do so in that much easily. Eventually, so stability order will be A greater than B greater than C. No confusion in that. Actually, the carbocation C is not formed at all. Why? There is a special rule called Braid rule. B-R-E-D-T. Braid rule. Braid rule says any bridgehead position cannot attain sp2 carbon. In bridgehead position, sp2 carbon is not possible. sp2 carbon, where we can see sp2 carbon? At carbocation is sp2, and alkene carbon is sp2. So at bridgehead position, carbocation or alkene cannot form. What is bridgehead position? This type of system are actually bridge compounds. Here, this particular carbon, it is in bridgehead position. This particular carbon is bridgehead position. Second structure like this. Here, this one is bridgehead position. This one is bridgehead position. This second structure and this structure is similar. If you watch this second structure from above the plane, it is similar than this. Okay. Third one, if I draw like this is also bridge. Okay, this is also bridge. Now here this is positive charge, positive charge, positive charge, suppose. So these all are bridgehead position. Bridgehead position cannot attain sp2 carbon, right? Because bridgehead position cannot attain sp2 carbon, sp2 hybridization, because if this center has to be planar, then this bond and this bridgehead bonds will have very high strain. You can assume that if this bond, and this bond has to be planar, and simultaneously the backside, this bond has to be planar, then what will be the what will be the fate of that particular carbon, that particular knot? Okay, knot means I am saying KNOT, knot. Okay, so that particular knot will be bleached, will be broken, will be destroyed. So there will be high strain. That's why bridgehead position cannot attain sp2 center, sp2 carbon atom. Now, this first bridge is 2-2-1 bridge. Here is 2 carbon, this side is 2 carbon, here is 1 carbon. So it is 2-2-1 bridge. Second one is 2-2-2 bridge. Second one is 2-2-3 bridge. 1, 2, 3. 2-2-3 bridge. So if we compare the stability, then this will be stability order. From A to B to C, stability is increasing. Why? Because when we are increasing number of atom in the bridge, then the flexibility is increasing. From A, B is more rigid, flexible. From B, C is more flexible, because we have increased number of atom. More number of atom gives more flexibility. Okay, so though bridgehead position cannot attain a positive charge, but if it is given in question, you have to go with that. You have to consider flexibility in this way. So this is basically flexibility issue with carbocation or with bridgehead position. Now, a very beautiful comparison we have to look upon. In this comparison, we will be comparing different effects. Okay, when suppose in some cases more number of hyperconjugation is happening, does it override the resonance? Can it give more stable? Can it give more stability than resonance? We are going to look upon those examples. Okay. First, let's clear the board. Clear all drawings. Okay. Okay. So we are going to compare resonance, all examples with resonance. We are going to make a series where we are going to compare resonance, hyperconjugation, aromaticity, dancing resonance, etc. Let's quickly understand what dancing resonance is. There's a particular cation, this cation. This is called cyclopropyl methyl cation. This is cyclopropyl group. This is methylene carbon, methyl carbon. It is cyclopropyl methyl CPM, cyclopropyl methyl cation, CPM cation. So this is very much stable, very much stable. Why? This is called here this system, the phenomena occur called dancing resonance or sigma bond resonance. Sigma bond resonance. Sigma bond resonance. What happens here? This sigma bond is undergoing resonance here. This here positive charge. Again, if this sigma bond undergoing resonance, then another structure will be this. So this is sigma bond resonance. When we study resonance, then everywhere we have seen that pi bond is doing resonance, but this is sigma bond where the resonance is being done. This is because actually this triple bond, this hybridization is not exactly what it is showing. The cyclopropane ring, it has a different kind of different kind of stability. That is sometimes it is called sp5 hybridization. This is very interesting phenomena. I have already made one video on that, how this is something can be sp5. There's only 3 p orbital we have seen, right? So how can 3-member ring can attain sp5 hybridization? I will try to give a link of that video in the description. Okay, you can watch that. Okay, so let's come to the point. So this is sigma bond resonance, and this gives very much stability of on a carbocation. This carbocation is very much stable. It is more stable than even aromaticity. Majority of aromaticity, it is more stable. Now, with all these phenomena, dancing resonance, aromaticity, hyperconjugation resonance, we are going to make a series that will clear all your confusion about some carbocations with those everywhere there is a conflict. And the series I am giving to you, the different part of series are from different standard books, just I have combined them. So in the entire series of carbocation, the carbocation the most stable carbocation is this one. Let's make a different section like that. Wait. Here we are going to write all the relative stability of different carbocations. Okay. Most stable carbocation is 3-member ring, positive. This, if we make it positive, this is actually aromatic carbocation, but no, this is not the most stable. Most stable carbocation is if we give 3 cyclopropyl methyl group here. This is most stable. So this positive charge will resonance to this point, to this point. So everywhere when it is undergoing resonance, it is getting the dancing resonance that is making the system most stable. Sorry. Okay, that is giving the system, that is making the system most stable. Second, after that, the carbocation which is most stable, this is the most stable. Okay. Now, when there is 3 dancing resonance with 1 carbon, that will be very much stable. Okay. Then if there is two dancing resonance, that will be very much stable, right? Now, if there is one dancing resonance, will it be more stable than this? Oh, will it be more stable than this carbocation? This is aromatic, tropylium carbocation. No, this will not. After that, after these two, there will be tropylium carbocation. Okay. After that will be 1 CPM group. No, after that, that is triphenyl, phenyl, triphenyl methyl carbocation. After that, 2-phenyl carbocation. Okay. So first this one you can easily remember. So these two, 3 CPM. Oh, this will be CH3. This will be CH3. So first 3 cyclopropyl methyl group, 2 cyclopropyl methyl group. Then tropylium. Then this 2. Okay. After that, your 1 cyclopropyl methyl group. This. Okay. After that, 9 hyperconjugative structure. This is 3-degree carbocation. 3-degree carbocation with 9 hyperconjugative structure. This will be more stable than even benzylic cation. Benzylic cation, you can assume that it is very much stable due to 3 resonance of 6 pi bond. But even 9 hyperconjugative structure is very much stable than this. Okay. But if these two are very much similarly equally stable, but this 9 hyperconjugative structure is slightly more stable. This is 3-degree carbocation. If we make another 3-degree carbocation with not 9 hyperconjugative structure, less than 9 hyperconjugative structure, then this will be less stable than this. For example, this one 3 to 6, 8 hyperconjugative structure. 8 hyperconjugative structure, this will be less stable than this. So these two has almost similar stability. In some sources, it is given that both have similar stability, but some studies, DFT studies says that this is more stable, slightly more stable. After that, it is coming our aromaticity with simplest aromaticity, aromatic compound, cyclopropynyl cation. After that, allyl cation, it is resonance. So you can see that 9 hyperconjugative structure is more stable than even resonance, and even resonance and aromaticity. Okay. Next, 2-degree carbocation. Next, 1-degree carbocation. Next, carbocation on double bond, and least stable is carbocation on triple bond, you know. Okay. So this is the entire scheme. Okay. This section is the most important actually. This section. And don't confuse with that. 9 hyperconjugative structure, 3-degree, but less than 9 hyperconjugative structure, this cation, this thing. Okay. So don't get confused. Sometimes randomly, in random examples, suppose this one, this one, this one, you will make that logic that it is okay, it is resonance, this is only hyperconjugation, this is resonance, this is more resonance, so that will be more stable, like this should be order. No, very carefully write this order in your notebook and practice with writing. Try to memorize it, I can say, but these are actually the order. Some things you have to memorize sometimes for cracking exams. These are actually these have logic, but overall, when there is a difficult question, when they are giving all mixing up together, uh, logically or ethically, they should not we cannot compare different things. Okay, we can't compare a pen and a notebook. Okay, both have different values, so comparison should be done between similar things. So in a series of compound, if they are doing variation in aromaticity, that should not be mixed with hyperconjugation, etc. So always we should compare with similar kind of things, right? But if examiner gives comparison with the different versatile things like dancing resonance, aromaticity, this should be the order, and that you should be taken care of. And after this video onwards, we will be going to rearrangement ring expansion, etc., ring expansion, contraction, addition reaction, name reaction. Okay, so till then, bye bye. If you have any doubt, you can comment below. I will be replying. Okay, thank you.